This is my 7th electricity video, and it's on EMF and internal resistance. Now look at these two circuits. We have a power supply and a resistor, but in the first circuit, the switch is open, and in the second circuit the switch is closed. So in the first circuit we are not drawing any current. In the second circuit we are. A current is flowing. And looking at the voltmeter reading, in the first circuit the voltmeter reading is 6 volts. When we close the switch it's only 5.8 volts. When we draw a current from the power supply we get less voltage from it, and that's due to internal resistance. Okay, so explaining it, when the switch is closed, what energy transfers are taking place? Well, in the cell what's happening is that chemical energy is changing into electrical energy, and if it's a 6-volt cell then that's 6 joules per coulomb, and that's called the EMF of the cell, the electromotive force. The EMF of the cell, which has this symbol squiggly E, is the EMF of the cell is the total energy transferred per coulomb from chemical to electrical. In the external circuit then there is a voltage. Let's imagine it's just a resistor. Then the voltage across the external circuit is the energy transferred per coulomb from electrical to heat, and that's just going to be 5.8 joules per coulomb, and we call that the terminal PD. So the terminal PD is how much voltage the external circuit gets, or how many joules are transferred per coulomb in the external circuit. So basically what's happening is that we're losing 0.2 joules per coulomb, so that must be being transferred somewhere else. Going back to our petrol station analogy, the EMF is the petrol that is given to each car at the petrol station. The terminal PD is the petrol used up by each car as it drives around the circuit, and my lost volts, my 0.2 volts, is the petrol used up driving through the petrol station, and that's actually the energy transferred due to the resistance of the cell. Okay, here's an equation here. My EMF equals big V plus little v. EMF is the total energy transferred per coulomb. Big V is the energy transferred per coulomb in the external circuit, and little v, my lost volts, is the energy transferred into heat in the power supply, because the power supply has resistance. Not very much resistance. We call it the internal resistance of the power supply. Okay, rearranging this equation we get V equals EMF minus, and instead of little v I've written I little r, where I is the current and little r is the resistance, the internal resistance of the power supply. Looking at this graph here, basically the more current that we draw, the less voltage we get. Now why? Because looking at the equation, V equals minus IR plus E, the bigger the current, the bigger the lost volts. So the more current we draw from a power supply, the less voltage that we get from it. This is an important graph which you definitely need to know, and one of the experiments that you need to know is how to go about getting it. And what you do is just put a variable resistor across a cell, and then measure the voltage across the cell and the current coming from the cell, change the resistance, take readings of V and I, and plot them. Looking at V equals minus IR plus EMF, that's very much Y equals MX plus C, so that tells me that the intercept is the EMF, and the gradient of the graph is going to be minus R, where little r is the internal resistance of the power supply. And interesting also that from this graph you can find out the maximum current that this power supply can deliver, called the short circuit current. Now, these two batteries both have an EMF of 12 volts. There's the big, massive, heavy car battery. That's a 12-volt battery. And then there's another one. I've been through all my remote controls. I've got all the AA batteries. I've put them together. So both of them have an EMF of 12 volts. Could they both start my car? My car needs 100 amps. The starter motor needs 100 amps to get going. And the answer is no. Now, why not? Because basically all the little AA batteries put together will have a very big internal resistance. Its internal resistance will be very big. The maximum current that it can deliver will only be 1 or 2 amps at the most. The car battery, the big meaty car battery, has a very small internal resistance, perhaps about 0.1 ohms, and it can give me lots and lots of current. Not for very long, but for long enough for me to be able to start my car. Here's a question for you to have a go at. I'll not tell you the answer. I will show the answer in 3, 2, 1. And there you go.